Hello, you all. Let's talk about functions. Last week we talked about the most popular function, linear functions. Now let's get into all types of functions. And first, we're going to just take a quick review of function notation and some vocabulary that you need to know when you do operations with functions. So let's start. All right, let's start with some definitions. A blank is the relation in which each element in the domain corresponds to exactly one element in the range. And what that is a function. Okay, so a function is this relationship in which each element in the domain corresponds to exactly one element in the range. And this is also called a one-to-one relationship, okay? A one-to-one relationship. Now, in order to get more understanding of what a function is, we probably are, we're not confused, but we're probably wondering what these words mean here, domain and range. And most of you have heard this before, but the domain is going to be the set of all possible x values, and the range is going to be the set of all y values. And how I remember domain and range is I just remember math kind of works alphabetically. So D in domain comes first in the alphabet, and R comes next in the alphabet, just like X and Y. X comes first in the alphabet, so domain starts with the D and is first, and X is first. And range comes next, and that starts with a Y. So that's how I distinguish those two when I'm talking about domain and range. All right, let's move on, and we're going to talk about this relationship of functions and how it works. Okay, there are four ways to represent functions. And the first way to do that is with a mapping diagram. And I know you all have seen pictures like this before, where we have our domain values mapped to our range values. A mapping diagram shows a function if each element of the domain, that's what we're going to put in here, maps to only, and let's put that in only one element of the range, okay? And we're going to talk about this, but basically my domain, which is my X, maps to only one element of my range, which is the Y. So we see that happening here. Now, if we go down here, this mapping here shows an example of what's not a function. My X's are mapping to more than one element of my Y's. And now I remember this because I think about my X's, right? Think about your X's and why they're your X's. You don't want an X that's with you and somebody else, okay? That is not a good deal. That is why they are X's. So this is exactly an example of what is not a function. So let's look at this mapping diagram that does not show a function if one element of the domain, so we're going to fill in domain, maps to more than one range. Okay, so if one element maps to more than one range, it is not a function. Okay, I can list ordered pairs, and I know that an ordered pair shows a function when the domain values do not repeat. Okay, so our domain values are not repeating. And again, I go back to my X analogy, right? All of my X's, right? These are good X's if they only have one Y, okay? Now, if we see ordered pairs that don't show a function, well, it doesn't show a function if we notice that our domain values repeat. Yeah, not so good X's. We don't want them if they're with another Y. So if we see that repeat of the X, we know it does not show a function. The third way that I could represent a function is by using a table. Now, a table shows a function if the X value does not repeat. Okay, that's how we know that it is a function. If the X value does not repeat. On the contrary, if we notice that the X value does repeat, then we know it is not a function. So a table where the X values do repeat is not a function. If I look at my table quickly, I notice I got good X's up here, right? They're all different. They're going to a different value. But if I look at my table over here, this is definitely not a function because I have X's, two X's, the ones are going to different places. That is not a good look. Okay, not a function. Okay, the last and final way that a function can be represented is through a graph. Now, to the left, you see a graph that we know is a function, our linear functions. How we know a graph is indeed a function is if it passes the vertical line test, okay? A graph does not show a function if it does not pass the vertical line test. Now, what's the vertical line test? Well, that means that I've dropped in these vertical lines, and when the vertical line hits the function, or the graph in this case, the graph is the function, it's only hitting the function one time. So notice each vertical line is only hitting this line one time. That's why we know a line is a function, because it passes the vertical line test. They give us this line over here of a supposed function, right? But we know it's not a function because when we drop in a vertical line here, the vertical line is hitting right here, it's hitting here, and it's hitting here. So if that same vertical line is hitting the function in more than one spot, that means that it is not a function. That's what happens here. So we know that this is not a function. We do the vertical line test. If that vertical line hits the graph in more than one spot, we know it is not a function. Okay, now it's time for me to try, and let's see if I can figure out if each of the following is a function. First example is a graph. We know with graphs, we need to drop in a vertical line and see if that vertical line hits the function more than once. And I notice it does hit the function more than once. It's hitting the function here and here. So this would not be a function. Nope. All right, let's look at this next one. Again, another graph. I want to know if it's a function, so I drop in a vertical line. Vertical line's only hitting once. I can drop other ones. Yep, still only hitting the graph one time. Every time I drop a vertical line, it's only hitting the graph one time, okay? One time. So is this a function? Yes, absolutely. Okay, now we see a mapping relationship. Is this mapping relationship a function? Remember, I need to see that I have good X's, okay? Good X's mapped only to one Y. And if I look at this, 2 is not being a good X. So this is not a function because it's mapped to two different places. This would not be a function, okay? So I want you guys to take a second and you are going to try. Okay, so what did you get? First example shows an ordered pair, and if we look quickly at our x's, every single one of our x's are different. This is a function. If we look at the next one, we have a nice little table. We're going to look at our x's and make sure we don't have any repeating x's. And notice I got 2 x's that are repeating. Not a function. Okay, so what is the domain and range of a function? Well, we talked about domain as all the x's, the set of all the x's, and range is all the y's. So if they ever ask you to find the domain, you're just going to do that. You're going to list all of the x values in a function. And if I look at this function, the domain is all of these x values. How I do that is I'm actually going to write the word domain. I will put a colon and then I'll put a bracket, and I'm going to list all of the x values from least to greatest, okay? So not from least, but least to greatest. Here we go. If I look, in my x values, I have 2, 3, 4, and 6, and they're already from least to greatest. So I'll have 2, 3, 4, and 6, and then I'll end it with a bracket. Okay, I'm going to do the same if they ask me the range. Range is my set of all y values. So again, I'll list my y values from least to greatest, semicolon, bracket, and I have a -3, -1, 3, and 6. Now, a couple things that I want you guys to notice. If you see, we know this is an example of something that is not a function, okay, because the x's are the x is cheating over here, number 2. But let's talk about it. If you see a value repeat, whether it be in the domain or whether it be in the range, we're only going to list it once, okay? So we are not going to repeat that value twice. Take a second. I want you to find the domain and range of problems 3 and 4. Okay. So if we look at this function, the 2 examples that they give us, we see this is a function, which is awesome. If I list the domain 1, 2, and 3, and then the range, be careful listing the range. We want to make sure we have it in order, -13, -5, and 3. Over here, this is an example where we have repeating domains. Again, we're going to list the domain 1 time. So I only list 1 once, okay? And then make sure you're placing your range in order. This would be an example of something that is not a function, all right? All right, you will see functions and they will be written like this. This is function notation. It actually means f of x. That's exactly how we're going to say that. F of x. All f of x means is y. Okay, so this is just another way to write y. So if I look at example 3, it says given f of x is equal to -4x plus 1, write the value of f of -2. All this means is if I input to the function a -2, what is the answer going to be? So if I input for x a -2, what is the answer? So to do this operation, we are going to evaluate the function at the particular value by simply doing this. We are going to put in the value for the variable and do the calculation. So what that means is we're going to simply put in the value in the parentheses, -2, into this function for the variable and do the calculation. So I'm going to say f of -2. Notice I input that in. And I'm going to put -2 in everywhere I see an x. So 4 times -2 plus 1. Notice I input -2 everywhere I saw an x. Now I just do the calculation. Well, what is -4 times -2? Well, that's +8. So f of -2 is equal to 8 plus 1, which means f of -2 is equal to 9. Okay, now I want you to take a second, pause the video, and I want you to try. How did you do? All right, input -6 into the value where you see the variable, do the operation. You should have gotten f of 6 equals 13. Okay, right now we're going to do what's called operations with functions. So we're going to take this just a little bit further, and we're going to use our function notation using 2 different functions and do operations with them. Now for addition, you're going to see the function notation just like this. They'll give you a function f of x, they'll give you a function g of x, then they'll tell you to take f plus g, and this part right here just means of x, okay? We can do the same with subtraction. They'll say, hey, here's f of x and g of x. Now take f minus g of x, okay? Same for multiplication and same for division. And we're going to do just what they tell us to do. We'll take the function they give us, if we're adding, and add it to the other function. Subtraction will do the same. We'll take the function they give us and subtract it from the other function. Same for multiplication and same for division. All right. So let's go through the practice of all of those operations. They tell me to find f plus g of x, f minus g of x, f times g of x, and f divided by g of x for f of x and g of x. So I'm going to go through doing A and walk you through each one of the operations. I'm going to start with addition first. All right, when I add the 2 functions together, I'll substitute in f of x into the equation. I'll add that to g of x, which is x minus 5. Now I'm just going to do the operations, adding them together by combining like terms. I'm combining the like terms of 2x plus x, and then the -1 minus 5. So I end up with f plus g of x is going to equal 2x squared plus 3x minus 6. All right, now let's look at subtraction. When we subtract, we would be subtracting the 2 functions. I'm going to go ahead and just do that, simplifying in, or substituting in, for f of x, the function, and subtracting it from the function g of x. The big thing to remember with subtraction is that when you're subtracting 2 functions, you have that whole -1 that you have to distribute into your parentheses set. So when I rewrite this, I end up with f of x and then minus x plus 5, which is the negative of g of x. Okay, then I'm doing the same thing. I combine like terms by subtracting the functions, and then I end up with that f minus g of x is equal to x squared minus x plus 4. Now we'll move on and we'll talk about multiplying the 2 functions. So if we look at multiplication, we're going to simply substitute n for f of x and g of x and multiply the two functions. So if I look at it, I'll do just that. I substituted f of x, the function for f of x. I multiplied it times the function for g of x, which is x minus 5. This is when you have to use distribution, right? You got to make sure every single term is multiplied by every single term. So I did it for x, right? And I got x cubed plus 2x squared minus x. Then I did it for negative 5. Same thing. Distributed that to every term. I got negative 5x squared minus 10x plus 5. Then we'll do our last step of combining like terms. When I combine the like terms, I got f times g of x is x cubed minus 3x squared minus 11x plus 5. Now we'll move on to division. The key with the division too is to make sure that your function in the denominator, g of x, is not equal to 0. So as you notice up here, g of x can't be 0. Well, they gave us f of x and g of x. And again, this is substitution. In the numerator, I put f of x. In the denominator, I put g of x. And if I look at this function, I can't really simplify this any further. It is what it is. So this would be f of x divided by g of x. Now we're going to move on. You are going to try for problem B. I want you to pause the video, go through all of the operations, and then you'll check your work to see what you got. All right, go ahead and check your work. Did you get for f plus g of x, x squared plus x minus 72? Down here for f minus g of x, you should have gotten x squared minus x minus 90. For f of x times g of x is x cubed plus 9x squared minus 81x minus 729. The last one, guys, you should have gotten x minus 9 when you simplified it for f divided by g of x.